All right. So now our question is, how do we get the value estimate and the optimal policy? How do we get V star and pi star, which we just used to calculate this? And one solution is using dynamic programming. And dynamic programming is basically using the Bellman equation to reformulate a problem recursively into subproblems. And so we can now take our value estimate. Let me just copy this here. Oops. Okay, so this was our problem. We want to get the value estimate, and now we want to reformulate this. So let's rewrite that. We can rewrite this expectation of future discounted rewards as the sum over all possible actions of the probabilities under pi of the action given the state, multiplied with our transition probabilities, so the sum of the over the next states and rewards of the probability of ending up in state S bar, given that we are in state S and performing action A and receiving reward R. So, and then we multiply this with the received reward R plus the discounted value estimate of the next state, S bar, under the policy pi. Okay, so this here is the probability of actions under the policy pi. This part here are our state transition probabilities. And this part here is the current reward plus the discounted future reward. Also called return under policy pi. Okay. And now you can see we wrote this recursively. So now we have here a value estimate of the next state in the definition for the value estimate of the current state. And now we can solve this using dynamic programming. And there are two options for optimization here. The first one is policy iteration. And in policy iteration, we basically iterate between policy evaluation and policy improvement. So we have two steps. We want to get the policy, the optimal policy, and we want to get the value estimates. And in one step, we perform policy evaluation. And then in the next step, policy improvement, and then we repeat this. Okay, and in policy evaluation, we basically update our value estimate to the value estimate of our new policy. And in policy improvement, we make our policy greedy in respect to our new value estimate. So in policy evaluation, we make the value function consistent with the current policy. And then in policy improvement, we make the policy greedy with respect to the current value function. So we iteratively update the policy and the value. So basically, we start out here with just, I guess, a random value function and a random policy. And then we perform policy evaluation, policy improvement, policy evaluation, policy improvement, and so on, until this whole thing converges. And this is proven to converge and at convergence it also ends up as the optimal value estimate and optimal policy. All right, and here, so whenever we go here, we set the value to the value under the new policy, and when we go to this point, we set the policy to be greedy with respect to the new value that we just updated. Okay, and we can also, instead of oscillating in this really small point here, we can also use early stopping and avoid a lot of computation for not much extra improvement if we just need a good policy and not the optimal policy to save us some time. Okay, let's take a look at some pseudocode for this. So first of all, we need to initialize value estimates and a policy function for all states in the state space. So this is tabular, so we basically have a table with all states, and then we can look up the value for each state or the policy for each state. So it's a lookup table. And we can initialize this arbitrarily. And then while the policy is unstable, we want to keep learning. So first of all, we want to keep track of the change. I'll talk about this in a moment. So we iterate through all states. So for each state in the state space, we first save the old value estimate. And then we update the value estimate according to this formula that we just rewrote up here. So we take the sum over our next states and rewards of the transition probabilities. The probability that it gives us of being in, of ending up in the next state and getting the reward, given that we were in state S and performed action A. Oh, and action A, actually, we get this from our initialized policy. So this is the output of the policy given our state S. And then we multiply this with the reward plus the discounted value of the next state. Okay, so this is updating our value according to the current policy. And then we just need to check what the change was. So we just look if the absolute difference between the old value and the new value is bigger than our current maximum. And if not, we keep updating. Okay, and then we want to update the policy as well after we perform policy evaluation. So we save our old policy and we iterate again over all states in our state space. And now we update the policy. And this we do by picking the best action of all possible actions, determined by the sum over all next states and rewards of the transition probabilities multiplied with the reward plus the discounted value estimate of the next state. Okay, so this is updating our policy according to the new values that we just updated. And if the old policy is our new policy, then we didn't make any changes, and then we have a stable policy and we can stop doing our policy iteration, because now we have an optimal policy and value function. Okay. And before I go to the next option, I have another exercise for you. And this is, look at this algorithm and tell me which part of the algorithm is policy evaluation and which one is policy improvement. So if you remember here, policy evaluation, we update the value function to be consistent with the current policy, and in policy improvement, we make the policy greedy with respect to the current value function. So which part of the code is policy evaluation and which one is policy improvement? So think about this for a moment, and then you can join your breakout room and talk about it with your team and decide on which part is which. All right, welcome back everyone. I hope you had enough time to think about the question and come up with an answer. Let me know if I don't give you enough time. All right, so here's the answer. The first part, the one where we iterate over all states and then update the value of each state, is policy evaluation. So we update the values according to the current policy. And the second part, where we iterate over each state and then update the policy, we perform policy improvement. So we improve the policy according to the new values. So if you got both of those correct, give yourself 2 points on the race board. And yeah, Xenia was right. If you had the last question completely correct, you also got 2 points for that. So now you could be on the 4th space if you got both questions completely right, or on the 5th space actually. If you feel like you got only part right, just move ahead 1 space, or no space if you didn't get it. It's okay if you didn't get it. So if there are no questions, I'll go on. So the second option is to use value iteration. And in value iteration, the policy function is not needed because it can just be calculated from the values. So we are only iterating over the value function and optimizing that. And in practice, it's usually faster than policy iteration. And it's also guaranteed to converge to the optimal value function. So let's take a look at that. We also initialize an arbitrary value function in the beginning for all states in the state space, but we don't initialize a policy function. We don't work for that with that in this. And then we iterate over all states in the state space. Again, we save our old value function just to see if we are still making any changes. And then this is the important part. We update our value estimate of state S according to the maximum action. So the value is now determined by the best action that we can perform, not the action under our current policy. So the maximum action for the sum over the next states and rewards of the transition probabilities. And now here we use the best action, or we look for all actions and then pick the best one, and not like we did here in policy iteration, we use the action under the current policy. And then this again multiplied with the reward plus the discounted value estimate of the next state. Okay, and then we just check again what is the biggest change that we made so far, and if this change is smaller epsilon, we can stop optimizing. Okay, and then the policy, the optimal policy is then the argmax action of the above value equation. So that's a greedy and deterministic policy, just taking the action which leads to the best next value estimate. Okay, and dynamic programming methods perform bootstrapping, which means they use state value estimates based on estimates of values of successor states. So they update estimates based on other estimates. So that's bootstrapping. And now I have another exercise for you. Should be a bit quicker, so try to come to an answer within a few minutes. Think about this dynamic programming and what might be a problem with it. So imagine we have a robot vacuum in a real-world room, and it's supposed to learn an optimal policy. And we want to use dynamic programming to find this optimal policy and value function. And think about what might be a problem with this. And just as a hint, take a look at all the variables that are required for policy evaluation and policy improvement. So just take a look at what variables we need here and what you think would actually be available to us in this real-world robot vacuum scenario. And yeah, just talk about this real quick, what might be a problem here. All right, welcome back everyone. I hope you could all think of something. If not, that's okay too. Okay, so what could be a problem with this robot vacuum trying to perform dynamic programming to find an optimal policy in this real-world room? And the answer is that the environment dynamics are unknown. So we don't have access to the transition probabilities of the environment or the reward function for each state transition. So, I mean, you could also come up with other problems, like we are in a continuous state environment. But our main problem here is, if we go here, we don't know about these transition probabilities. We don't know if I'm in state S and perform action A, where I will end up and what kind of reward I will receive, and what are the probabilities for this. We have to find this out by experience. So we have to learn these transition probabilities and reward function. And in many practical examples, these environment dynamics are just unknown. And that's what the next topic will be about, which is Monte Carlo methods.